Missing formulas in life? Problems becoming too difficult to clear? Well then, you need Mr. Math Cleaning Solution.
Hey guys, Mr. Ing here. Just want to let you guys know that I love math. Well anyways, in 8.2 we're using statistical experiments. In 8.20 introduction here, we are going to have a learning target that students will be able to collect, analyze, and use theoretical and to compare experimental, whoops, that was wrong. To use data, information, to compare theoretical, zoom in here, theoretical and experimental probabilities. So that's what you should be able to do in practice after this video. Okay, I got a warm up here. Assume that you have cards labeled with the first 15 prime numbers and you draw a card at random. So let's make sure we understand what a prime number is. A prime number is a number you can only, that number is equal to a number times 1. So for example, the first one is going to be, the first prime number is going to be what? Is going to be 2, because 2 times 1 equals that number, 2. Or I'll give you another one. How about 49 is not a prime number because that would be like 7 times 7. Those are the other factors. So go ahead and press pause. Go ahead and do questions 1 to 5 and we'll go over those together. Number 1, what are the outcomes in the sample space? The hint is write the first 15 prime numbers out. And so the first 15 prime numbers are, it's not 1. So you have 2, 3, not 4, because 4 is 2 times 2 or 4 times 1. You have 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. So a review with your data, this one's really good, is that the numbers are from least to greatest, and you can help yourself out by writing the numbers on top. That's super helpful sometimes. 6, 7, 8, 9, 10, 11, 12. Whoops, that says 112. 13, 14, and 15. Okay? Okay, number 2. You draw a card containing the digit 7. What are the outcomes for this event? Outcomes is which ones can I pick? So which ones have a 7 in it? There's one, there's another one, 27 and 47. And I missed one, 37. So you have 1, 2, 3, 4 of these contain the digit 7. Question number 3. What is the probability that the card you draw will contain the digit 1? Okay, remember probability is all divided by the select that you want. Okay? So here we want the probability with the digit of 1 is equal to all of them. So there are, how many numbers do we have there? 15 numbers from up here. and then which ones have the digits 1 in it. So I see, I'll just write these down, 11, 13, 17, 19, 31, and 41. So that is 1, 2, 3, 4, 5, 6 of these. So 6 out of 15, and then we can just reduce this. 3 divided by 3 is 1, so your answer is 2/5. The probability they draw one card containing the digit 1 is 2/5. Okay, what is the probability that you draw? I think I have a typo here. That you draw 21. No, it's not a typo. What? Look at this. Here's the question. Where is 21 in this list of numbers? Well, from this number, the 15 prime numbers up there, can you select, is there a 21 in there? That would be a 0 out of 15. So that would be a 0. Remember, probabilities are numbers between 0 to 1 or 0 to 100%, because it's like, you know, you might have something like 0.2, 0.3, you convert it to a percent by multiplying by 100, but you can't even pick 21, so that would be a 0%. Okay, what is the probability that you draw an even number? Even number, okay. So even is just divisible by 2, divisible by 2, with no remainder, right? You can cut it in half evenly, as I might want to say. So let's pick a different color. So no, odd, even. So that would still be 1 out of 15 would be your answer for that last question on the warm-up. Okay, let's go over some vocabulary words. For example, number 1. And the first word that we need to go over is the vocab word theoretical probability. Theoretical probability. Theoretical probability is what is expected, and I'm going to highlight that word, expected. What is expected to happen? So for example, my wife and I, when we had our first kid, we really wanted a boy first. And the total, or all of them, there's only 2 genders, so that'd be 2, and then the select, what we wanted was a boy, so there's only, you know, between boy and girl, from the sample space, that would be 1/2. That is our expected 1/2. Each time that we have one of our 6 kids that we have. Okay, theoretical probability is what happened is what actually happened in reality. I can't spell reality. So I'll draw a sample space for each of my kids. These are my 6 kids. And then our first kid was a girl, right? And then you think the next one would be a boy. But then you're thinking next 1/2 would be a boy or girl, but I got a girl. And then the 4th one you expect, oh, maybe like a hot streak. No, we had another girl. And then 5th child, you know, you think, okay, you want another boy to even it? No, we had another girl. And then the 6th one was a boy. So you would think that out of all of these, you would have 3 boys and 3 girls, right? You expect the probability to be 1/2. But our probability of a boy, in our case, is 2 out of 6. So our experimental probability was actually 1/3. Okay? Let's move on to the next page. Okay, let me fill out some of this, and then I'll show you guys my video simulation. If you flip a coin, so you have heads, and then you have what? Tails, they call it. My kids have been drawing dinosaurs, so tail. And you would expect heads to come up 1/2 of the time. Whoops, we did heads in light blue. And then tails would come up 1/2 of the time. And the word expect comes back in green, so let's write that in green from above. This is called what? This is called our theoretical probability. Like our TP. All right, so let's go ahead and go to the my flipping of a coin. All right, instead of me flipping a coin a bunch of times, may not be very practical, so we use something called a simulation. The computer-generated model here. And right there, number 2, in my video example, or what I'm doing right now, is I use the computer to conduct a 100 flips. So write that in the blank, 100 flips, okay? And so I press this, and I don't actually have to flip the coin a bunch of times. So you would predict that if I had 100 flips, that it should be what? 1/2 of them should be heads and 1/2 should be tails. So 1/2 times 100, your expected value is equal to the probability times the total number. So you would 1/2 times 100 is 50 tails and 50 heads. But what happened? What did I get? 50-50 doesn't always happen all the time. So here I have 45 heads as my actual and 63 as my tails. The word predict, or the expected, and then the actual is which type of probabilities. Alright, so I use the computer to conduct this is called a simulation. I took my kids to a museum this summer, and you go on a simulator, and the simulator was to pretend that you're on this helicopter flying around Southern California. It wasn't real, just kind of computer generated videos right on a 3D screen, stuff like that. But I do that so I don't have to flip the coin. So in my last video there, I flipped it 100 times. And what I was talking about is in the 100 flips, well, if you want the probability of heads, or an expected value, you would do the total times the probability. So 100 is our coins. N just represents the number of items you have, and P represents probability. So if you did 0.5, you multiply that in your calculator. The trick for that is, you have 2 zeros, so you're going to move it 2 decimal places, 1, 2. So you would end up with 50. So you expect 50 heads and 50 tails. And then our actual there was we had 45 heads and 63. So question, what is the actual here from our definition vocab words up here? Is that the theoretical or experimental? Well, this was my experiment. So this is my experimental probability. In theory, or theoretical, that would be my TP, right? Because this is what we predicted. So, yes or no, this matched or did not match the theoretical probability. No. You can cross that off, cross that off, so no. Did not match the theoretical probability. This is called the experimental probability. In our experiment, this is actually what happened. And if you get bored, go ahead and take a coin and flip it 100 times and see what happens. And just to note, something really cool is that if you did this 100 times, 1,000 times, and let's just say that this is, ours was probably like, so this represents 45% and 63%. That doesn't even add up to 100. Maybe I stopped it early or something. Yeah, that doesn't even add up. Like, I just realized that. Let's erase that and do something that actually matches. So let's say it was this 55. Oh, it's erasing. 55. Okay, so let's just say this is percent heads. And ours was 45%. So let's say 0.4, 0.6, 0.7, 0.8. Do you think we can get 90%? 45% would be something like here. You would put a dot here. And let's just say the next time I ran it, it did 50-50. So 50% heads, I would put a dot here. And let's just say one time I did it, it was so crazy, it got 80, and 20. So 80%, there's my dot. And if you do this experiment, this simulation over, I don't know, 2 million times, you'll notice something. What you'll notice is that you'll get, it'll come all over the place, but what happens is that your dots will keep starting to stack, and you'll realize that they stack right here towards the theoretical probability, and they call this one the law of large numbers. The law of large numbers states that as a sample size increases, right, we keep testing this a billion times, the variation in data set decreases, meaning you'll go towards it. So as the sample size increases, meaning you do this a bunch of times, you'll closely resemble what the associated probability was.
Just spray the liquid formula onto the mess, then wipe it clear, and enjoy the result. Mr. Math. Stay clean and calculated. Order now at www.gpproductions.com and get an additional